Hello, good day. My name is Adrian Prasad.
And I'm Hannah Wang, and we're part of the Systematic Extension Technologies Design Flow subteam. And today we'll be talking about our work on OpenLane Design Flow. So some of the stuff we're going to be going over today is some background on Design Flow and how it relates to Socket. In addition, we'll be going over OpenLane and how we can integrate it into the design flows here on campus. In addition, we'll be talking about our project objectives and goals for this semester to work on OpenLane. I'll talk about some of the progress we've made throughout this entire semester and some next steps for next semester.
Okay, so the design flow is a really complex process that involves taking a higher level specification of a chip and then passing it through subsequent different file formats and multiple softwares that essentially make that higher level specification look more and more like a final layout file. And this layout file is essentially, you can think of it as having geometric data that specifies where transistors will be, the connections that wires have to have, and multiple and many other information that you can think of. So the process essentially takes something that's a really high level specification and produces a chip that can be handed off for lithography and what's called tape-out, which produces the actual chip. So this actual chip design and tape-out process is really complex. Over here, you can see a picture of just one of the transistors, which is a 3D design with multiple wires, multiple gates, etc. It's an extremely expensive process, and the software for the process is very proprietary. You can also think because it's a bunch of proprietary software that needs to work with each other, it's kind of you have a case of people writing together many scripts to bolt on software from one to the other. So there's no kind of very straightforward way to take a chip from a high level specification all the way to the end. So we are exploring something called OpenLane. OpenLane is a bit of an alternative to this process. It takes the entire design and runs all of the steps. It basically takes away all of the extra work that you have to do to bolt together all this software and works with a very simple single file that's usually a config.json or config.tcl script that will specify all the designs. It'll specify different metrics that needs to go through, and you just run that and it'll take your entire design from start to finish that hopefully can be taped out in the end. Additionally, because they take care a lot of that scripting together, they've been able to make some of the steps parallelizable so you can run it on multiple computers, multiple cores, so it can be hopefully faster than just running it on a single core. Finally, we'd like to present the team that we're on, Socket. Socket is a school team. It's made of undergrads, master students, all their graduate students that are all working together to build entire chips through from a high level specification all the way down and then send them off for tape out. Our current design is this AFT X07 chip, which you can think of it as a microcontroller chip. It's completely designed in-house at Socket and gone through an entire process of high-level specification all the way down to the tape-out process. However, Socket uses proprietary software that we've been licensed to under educational license, and it's really complex to use the software. It's unmaintainable in some cases as we're using older software and we can run into a fair amount of bugs.
So some of the project objectives for this semester is to use OpenLane as specified earlier to deliver a GDSII file, basically a layout file of the AFTX07 that was mentioned previously, and also the flex counter design, which is the basic design as well, using OpenLane, so using the automated design flow in order to generate this layout itself. In addition, not only are we generating layout, which design flow also does, we'll also be doing timing analysis, power analysis, generating those sorts of reports with OpenLane, and then reading through those files and seeing if they're correct according to the software we have already used with tertiary software as well. In addition, another goal of ours is to basically create an automation script to run OpenLane and move configurable files around, move the SV and V files around, so that's easier for students to be able to use OpenLane and use it autonomously as well. And so some current progress we've made. First off, we've been able to set up this OpenLane. So this first slide on the left, basically it's the layout of the smoke test SVM V file that's found in the OpenLane tutorials. So we're able to get that working on our own personal machines and get that working with the overall layout and timing for ports as well. In addition, we ran the smoke test and we ran OpenLane with the top level GDS, which had been created by some of the socket members in our team, and was able to create the layout, the timing reports as well for that. So you can see on the right here that those are the layouts of the ships that we are working on. And the top level not only, does the top level of the first Verilog file itself, it also takes another Verilog file such as a synchronizer and a flex counter, and so combines all of those different gates and chips to create one big top level chip itself. And so some other progress that we've made over this semester that we've been able to work on is basically create an automation script to move different SV files and VB files to the OpenLane setup in Nix to basically be able to run OpenLane synchronously all at one step. So it'll take two arguments basically where the original SV and V files are and which design you want to run. So first it works off the original config JSON file that you see on the left and modifies it to have an ALU or processor, whatever arguments you want it to have, whatever arguments you want it to run. And then after modifying the config JSON file and moving all the SV files to the Nix OpenLane repository itself, it actually runs OpenLane for you and generates the layout files and all the timing reports and static analysis as well. And so the overall result is the layout that was created here with the flex counter, and we're working on modifying our files from SV to V to account for Verilog headers as well. And so that's some of the current progress we've made. Definitely looking forward to integrating this into larger designs as well. And so some next steps for this is to basically work towards integrating OpenLane into larger designs. So AFTX07, adders, that sort of stuff. We're working on integrating that into helping with the tape out of the entire chip itself. In addition, we're running into some software issues with larger libraries like Verilog headers and that sort of stuff. So keep on debugging all of those major issues to make it easier for students who are using it in the future to be able to use and give them a tutorial on how to use it. In addition, creating scripts not only to automate the process as seen previously, but also to help with the setup of OpenLane itself and also set it up on ASIC Fab as well, the socket server that we use for all of our designs. That's one of the steps we're working to as well. And also because the design flow of OpenLane, it's made of different modules, static timing analysis, layout, power analysis, that sort of stuff. If we can parallelize the process of all those different analyses to make it run faster, we're also going to be working on that next semester as well.
Yeah, and with that, we're done. Thank you for listening.